third important factor in determining the rate of SN1 and SN2 reaction rates, nucleophilic alkyl substitutions, is nucleophile strength. And nucleophile strength is a little bit more complicated than leaving group ability, which track directly with acid strength. The conjugate bases of strong acids make good leaving groups, and substrate structure, which could be explained in terms of sterics and hyperconjugation. In the case of nucleophile strength, we have to consider more than one factor. In general, better bases are better nucleophiles. So, for example, hydroxide ion is a better nucleophile than water. Hydroxide ion is in fact the conjugate base of water. And because it's the conjugate base of water, obviously it's stronger as a base than water. It has a negative charge, water is neutral, going to be a better nucleophile. And in gas-phase reactions, fluoride is a better leaving group, or a better nucleophile rather, than chloride. And chloride is better than bromide. And bromide is better than iodide. So as the acid strength increases, the base strength decreases, and you see a slower rate of reaction. So in general, better bases, better nucleophiles. Negatively charged bases usually better than neutral, and the conjugate bases of weaker acids are generally stronger bases and therefore better nucleophiles. But there's more to it, because in a protic solvent, chloride ions is reversed. Iodide is a better nucleophile than bromide, and bromide is a better nucleophile than chloride, and they're all much better nucleophiles than fluoride, which in protic solvents like water or nucleophiles. So why is fluoride such a bad nucleophile in a protic solvent, where its basicity suggests that it should be a pretty good nucleophile, and in the gas phase reactions or completely nonpolar solvents, it is the better nucleophile, as you would predict from its base strength. What's going on in a protic solvent? And in a protic solvent, what you have to do is you have to consider that it's a pretty large ion with a relatively diffuse charge. The water molecules are going to attach themselves in the solvent shell. You're going to get solvation, where the partially positive hydrogen N is interacting with the negatively charged iodide. Form a solvent shell. But with a large ion like iodide, that solvent shell is relatively weakly held. Coulomb's law is, as always, present in Coulomb's law. constant times the magnitude of the positive and negative charges, partial positive on the hydrogen, negative 1 on the iodine, divided by the distance squared. And if you have a large distance, because you have a large anion, you're going to have a relatively weak ion dipole force. And therefore a relatively weakly interacting solvent shell. Compare that to chloride, for example, which is significantly smaller. To the water molecules that surround it. And thus form a stronger, tighter solvent shell. And now consider the case of fluoride ion, which is very small and holding its electrons relatively tightly. Fluoride ion surrounds itself with molecules of solvent, just as the others do. But because that bond is so strong between fluoride and hydrogen, right? Hydrogen bonding in this case, it polarizes the water to a large degree. So you get these partial negative charges on the oxygen. And those partial negative charges on the oxygen are capable of, in turn, attracting a second shell of water molecules. So you don't just get a single solvent shell, a double solvent shell, where the fluoride polarizes the molecules of water in the first solvent shell to create a second solvent shell. The combination of the fluoride and the water molecules in its first solvent shell is actually probably similar in size to the iodide ion by itself. So you get a second solvent shell from the polarization of the water molecules that are directly attached interact with the fluoride. Polarization of the water molecules that directly interact with the fluoride attracts a second solvent shell. It's going to be difficult for fluoride to escape from that double solvent shell, and escaping from that double solvent shell is what it has to do if it wants to react with the carbon of a substrate. Iodide will have a relatively easy time. Right? So in protic solvents with ionic nucleophiles, the solvation effect is more important than the basicity. The weaker solvent shell on iodide allows it to be a better nucleophile with a strong solvent shell on fluoride. This solvent effect here is only relevant to anionic nucleophiles. And it requires a protic solvent, something that has a hydrogen, which is small and relatively positively polarized, that can interact strongly with the anion. So in the absence of solvation, better bases, better nucleophiles, negatively charged nucleophiles better than neutral. In the presence of solvent, the anionic nucleophiles, if it's the right kind of solvent, have their nucleophilicity attenuated by the degree to which they're holding their solvent shell. For neutral ethers tend not to behave as nucleophiles. They're often used as inert solvents. But the corresponding sulfur and phosphorus compounds are quite good as nucleophiles. So dimethyl sulfide is a much better nucleophile than dimethyl ether. And phosphine is a much better nucleophile, in this case triphenylphosphine, is a much better nucleophile than the corresponding nitrogen derivative would be. I'm just going to write R groups. So relatively speaking, phosphorus and sulfur are better nucleophiles than nitrogen and oxygen. Neutral nitrogen is capable of being a nucleophile. Generally, it requires a relatively unhindered substrate. Neutral oxygen virtually never behaves as a nucleophile, although it can be protonated readily. But neutral sulfur and neutral phosphorus compounds are often good nucleophiles. You can, in fact, react dimethyl sulfide with iodomethane and that reaction proceeds rapidly to form a sulfonium salt, where you have 3 methyls attached to the sulfur and a salt. Triphenylphosphine, PH3P, reacts readily with alkyl halides to form phosphonium salts. Much faster than the corresponding nitrogen compound. So we need to understand what it is about those larger, more polarizable atoms that makes them better nucleophiles. And you'll notice this is the opposite of the basicity trend. The nitrogen is a much better base than phosphorus. Oxygen is a better base than sulfur because the conjugate acid of the sulfide is a significantly stronger acid than the conjugate acid of the ether, right? So it's polarizability. Polarizability is the key, but why should polarizability have an effect on nucleophile strength? And to understand that, we need to look at the orbital interactions that are involved as dimethyl sulfide, for example, with its 2 lone pairs, tries to interact with the substrate. So we know that the orbital that it wants to interact with is the LUMO. That's the empty orbital. And we know that that LUMO has a node along the carbon iodine. And we've got our hydrogens attached, although they're not actually important. In order for this reaction to occur, the sulfur has to donate its electrons into that LUMO. Because the orbital on sulfur is quite large, it can reach out at a relatively large distance of separation between sulfur and carbon and begin to donate electron density into the LUMO orbital. And as soon as you donate electron density into the LUMO orbital, you start breaking the carbon iodine bond because the LUMO orbital is anti-bonding with respect to the carbon iodine bond. Compare that to oxygen, right? With its much smaller orbital, still trying to donate into this carbon LUMO. But now oxygen has a significantly smaller HOMO orbital. So at that same distance of separation, the oxygen orbital is not large enough to reach out and put any significant amount of electron density into the LUMO. In order to get that reaction to occur, the oxygen is going to have to move closer to the carbon, so that it's then close enough to donate electron density into the LUMO. If the oxygen needs to move closer to the carbon before its lone pair can reach the LUMO to start putting electron density in, it will also move closer enough to the carbon that there will be some nuclear repulsion. And we know that the reason the fluorine-fluorine bond is much weaker in diatomic fluorine than the chlorine-chlorine bond or bromine-bromine or iodine-iodine bond is because of increased nuclear repulsion when you take those two second-row elements and move them close enough together that they can attract each other's electrons. Carbon and oxygen are both second-row elements. If you move them close enough together, those nuclei are going to start repelling. Sulfur, right? Sulfur is much more polarizable, much more diffuse. Its electron density can reach out further, and you can keep the sulfur and the carbon further away from each other as you begin to put electron density into the LUMO and thus weaken the carbon-iodine bond. And of course, the weaker the carbon-iodine bond, the more that bond starts to break, the larger partial positive charge you start seeing on the carbon, and a large partial positive charge on the carbon is going to further attract the electrons from the nucleophile. Right? You can think of oxygen as the big dumb linebacker. I mean, it doesn't really want to move very quickly. Or, you know, the defensive lineman rather. Right? It doesn't really want to move very quickly. Right? It would much rather just be able to stay where it is. Sulfur doesn't have to move. Right? Sulfur can push its electron density out there and start that reaction without having to go anywhere. Nuclei are big, right? To move a nucleus requires significantly more force than to move the almost massless electron by comparison. So polarizability is an important factor. It's an important factor because it allows the transition state to happen earlier as the electrons reach out at a larger nuclear separation, right? We've gotten less far along the reaction coordinate at this larger nuclear separation. That's an earlier transition state that lowers the energy of the transition state and allows the reaction to proceed more readily than where you have to have a later transition state and move the oxygen closer to the carbon before the reaction can begin. Only important in neutral nucleophiles. So for nucleophiles in nonpolar solvents or the gas phase, basicity is the most important. Anionic nucleophiles are better than neutral nucleophiles, and the stronger conjugate base, the stronger nucleophile. In protic solvents with anionic nucleophiles, you'll find the degree of solvation being the major factor, and the small, tightly held solvent shells will decrease the reaction rate. The second row elements like fluoride and hydroxide are actually going to form double solvent shells, which really decrease the reaction rate. And then for neutral nucleophiles, you'll find the third row and fourth row elements being much better nucleophiles because of this increased polarizability.